from the worksheet that I had you guys working on. So it does go pretty hand in hand with the images of your textbook pages. So if you had a hard time following through, you can always look at your textbook pages again, or this will also be posted as a PDF, so you can just look at just the answers. So most of this I do already have written out because these are lengthy problems. So I'll be explaining them, I'll be zooming in and out of them, and obviously this will be posted so you can always go back and look at a specific problem. So let's start up with what sigma notation is. Get rid of that. All right, so sigma is something that you might have seen before. Sometimes it's touched on in like the end of Algebra 2, maybe a little bit in pre-calc. But when you're looking at something that is a sigma notation, that's really what's called a summation. And that helps you get a better idea of what its purpose is. You're adding up and you're summing every single term. So when you break this sigma notation down, there's a couple little variables here. I is the index of summation. A sub I means it's the ith term. Okay, so whatever number I is, that's the term it is. Little m is your lower bound, which is kind of like your starting value. And then little n, like Nancy, is your upper bound. It's your ending value. So where you start, and then you just keep inserting the values, and you go up until you get to your upper bound. So let's look at a couple examples of sigma notation. So remember, you're plugging in your values for the I or the J or the K, whatever the variable is or the index. So for A, you see here that there's actually no variable, right? I'm going to add 2, and then I would plug in 1 wherever I could, but I don't have anywhere to plug it in. So I'm adding 2. I'm adding 2 again. I'm adding 2 again. And you can see that it really just ends up being almost like 2 times 10, which if you think about when you learn multiplication, it's really just a repetitive sum. So 20 would be the answer for A. Now you can see on part B where we're actually inserting those values. So we have I. So our first one is where we plug in 1 for I. Then we're going to plug in 2 for I. Then 3 for I, and 4 for I, and 5 for I, and 6 for I. And then you sum them up. So it's a summation. So you plug them in individually. So this is 1, 2, 3, 4, 5, 6. And then after you do that, you add it up and you get 21. Let's look at a couple more together. So if we go down, I'm going to go down to D. You can see now I have 3i. So as I'm plugging in values, you can see that you're starting at 2, and you're going to plug in values until you get to 5. So starting at 2, ending at 5. So we have 3 times 2, 3 times 3, 3 times 4, 3 times 5, 6, 9, 12, 15. Add them up, and that's your summation. Same idea for E. We're plugging in starting at 1, ending at 5. So you get that. Now for F and G, it's a little bit different because now we don't have an ending value. Okay, you can see that the value on the top of the sigma is really n. So it means it could be anything. N is a number. K is the variable. So when you're plugging in values, you're going to start at 1, then plug in 2, then plug in 3, then plug in 4, and whatever else would be in here, all the way until you get to n. Since we don't know what n is, you can simplify as best as you can, but your answer will still have an n in it, just like how this is our answer here. It's just simplified a little bit. That's all you can do. Same idea down here. Starting at 1, ending at n. So you have f of x of 1, x of 2, x of 3. You would have all the values in here all the way until you get to x of n. Again, we don't know what it is, so this is how your two answers stay. So I know it's a little strange. You don't really do a lot of work, but the notation is what's important. So that's the basics of summation, right? You're starting at a value, you're plugging in the next number, plug in the next number, and then add them up. Summation. We do have some rules and shortcuts. So on the top right-hand side here, we have a couple properties. Now the first one's kind of like that constant property. So we have this value k on the inside. It's not a variable, it's just a number. So if you have a constant on the inside, you can bring it to the front, just like how you could for like derivatives. When we started with derivatives, you could take the value of just a constant and put it in the front. Same for limits. For our property B, that's just the sum or difference property. So if you have multiple terms in your summation, you can separate them. And that's a nice way to visualize your steps as you go through. And you'll see that I'll do that in a lot of the problems so that you can really break it down and follow the steps. So here are your formulas that are going to make your life so much easier when you have values that are really large, right? Like if your n is 20, you don't want to have to plug it in 20 times. So these are kind of like shortcut formulas. So our first one is when you just have the summation of a constant, c. That was just like that example. That was just a summation of the value 2. So all you have to do is take that constant times n, so cn. Now the next three are pretty self-explanatory. So when you're trying to take the summation of I, or I squared, or I cubed, you can see that that's just what it becomes. So when you're taking the summation of I, it becomes n times n plus 1 over 2. And you can see the rest here. One of the most important things to remember is that this has to be where it's going from I equals 1 to n. Okay? It has to have this I equals 1 down here. This is so important to remember that if this is a different value, these formulas will not work. So let's look at some examples using these formulas. So these again are a little lengthy. I'll talk you through a couple of them, and then this will be posted so you can kind of pinpoint each example. So let's look at the first one. All right, so using our property, we know that n is just a constant, and we can bring it to the front. So I took that 1 over n squared just to get it out of the way. And you're going to see that being able to do this will make your work easier when you are switching these into your summation formulas. So I take the n squared out to the front, and now I just have I and 1. Using our second property where we can separate them, it helps us break it down so we're not really overwhelmed with what to do with this I plus 1. We can focus on just I and then just 1. So using your formulas, the summation of I is n times n plus 1 over 2. And when it's a constant, like a 1, you just do 1 times n. So it's a lot of algebra, and it's a lot of little mistakes can be made in the mix here. So you need to take your time, write out the steps. You need to be able to follow it through to make sure that you're not making a silly mistake in your algebra. So here we have where I just multiplied, make them have the same denominator, combine, and just simplify as best as you can. So n plus 3 over 2 is your answer. Now notice that I don't have a value for n, so I will have an n in my solution. I don't know what this value is. What's nice is if this is part A of a question, part B could say now if n equals 3 and n equals 6 and n equals 10, what would your summations be? And now you can just plug 6, 3, and 10 or whatever values you need into this, and you can skip this whole step again. So you kind of always want to pare it down as much as you can, and then if there's no value for n, your answer will have an n in it. So let's look at one that does have a value for n. Let's do C. So looking at example C, you're going to have to remember your rewriting abilities. So for instance, this is a binomial squared. You want to make sure that you FOIL that out and just have 3 terms to work with instead of kind of like a composite function. That's really what this looks like. Think about if you were trying to take the derivative of this, what steps would you take to rewrite it? So I rewrote it by foiling, and then you can see how I separated it. And that's using that property to help you see it more clearly, that it's a little bit easier. Okay, so separated. Using your summation formulas, we know I squared can be replaced by this. Now we know that I is n times n plus 1 over 2, and we still had a 2 in front of it. So you see I still have my minus, I still have my 2, and then this replaced the I. And I had 1n. So a lot of algebra skills in here to get it all combined. And you can see when you get to a certain point where maybe you can't combine anymore, maybe it's just not worth the effort, and you have the value for n, plug it in. Okay, so I plugged in 20, get the values, and simplify. So if you were to sit there and take the time and plug in 1, then 2, then 3, then 4, and do that all the way until you get to 20 and add them up, you would get 2,470. Okay, so I'm going to zoom out so you can see this page again. This will be uploaded, but you can see that you have, all the same ideas. It's just a lot of little algebra skills. One note that I put down here, which I already told you, is that if you do have a specific value for your n, you can evaluate the summation for that. So once you get to an okay point, or if you feel like maybe manipulating it a little bit more might cause an error, just plug in your n. Take your time. Use your orders of operations. All right, so on to page 2. So now we're going to use these summation ideas to help you finding the area under a curve. That's our big idea for this chapter, is being able to calculate the area under a curve. So you're going to see a lot that we try to use rectangles to kind of estimate these areas. Now, the reason that we chose rectangles, or that it's a common trend, is that rectangles are one of the easiest shapes to actually find the area of. It's just length times width. You can obviously see how rectangles aren't a perfect representation of the area. If we're looking at this image, you can see that the image that's in purple, or like that light purple shade, that's where our rectangles are covering, and the image that's pink, so there's kind of like these little wedges, that's almost like unaccounted for, right? So our big idea here is that if we can estimate the area under a curve, we can kind of like narrow it down. Our first 2 examples here are asking us to do this with 5 rectangles. Now you're going to see that after we do it with 5 rectangles, we do get a nice little range of what our area is going to be, but it's pretty big room for error. So you're going to find that if we create this with more rectangles, if we did this with 10 rectangles, it would get a little bit more accurate. And the trend would continue. If you were to do this with 20 rectangles, it would get more accurate. So for instance, to show you what it would look like with 10 rectangles. So if we were to cut this rectangle in half, you can see now it's a smaller little area. If we were to cut this rectangle in half, now we're including this area. And if we were to cut this rectangle, this is now included. This one's now included. So you can see we're minimizing that area, that's that unaccounted for area. So our big idea is if we create more and more rectangles, we can get a more accurate representation of the area under the curve. So you can see on here, now it's just these little regions. So this little pink region, this little one, it's a much smaller group of areas that we didn't count for. So let's go through what this would look like with 5 rectangles, and then we'll go over the difference with the 6. I'm just going to erase this so we can reference our image correctly. All right. So with 5 rectangles, first thing we need to figure out is our endpoints. So we have our endpoints, and they're at 2/5 I. And you can see that already on our graph. You have 2/5 times 1, 2/5 times 2, 2/5 times 3. And you can see that we go up until we get 2/5 times 5. So you can see we have I equals 1, 2, 3, 4, 5. The width of each rectangle, and you can find that literally by looking or measuring, just subtracting, right? If we just figure out, okay, how far is it from 2/5 to 4/5? That's 2/5. So the width of our rectangle is 2/5. And the height, that's what's going to change here. Our height, our value, our y value, will be the y value of the function. See how it's sharing that point of the curve? Y value of the function, the y value of the function. So what we need to be able to do is to plug our endpoints into our function and go from there. Now you could absolutely do this by hand and just try to like find those values, do length times width, and just keep adding them up. As you can imagine, if we had more rectangles, that's going to be extremely time consuming. So the summation and this idea of a summation helps us solve what it would be for 5 rectangles. And you'll see later on, we'll be able to do this for 25 rectangles. So this is a way that you can add up those values without having to sit there and just continuously do arithmetic. Okay, so when we get this set up, it's always going to be the function with the endpoints plugged in times the change or the width. So your length times width. So think about a rectangle, length times width. So we plug our value, our 2/5i. We're going to plug that into our function. Our function for this problem is negative x squared plus 5. So we have negative, this is replacing our x, squared plus 5, times the width, which is delta x, so 2/5. A lot of algebra will be involved again. So we have, you can see it over here, we square it, still have the minus in the front, plus 5 times 2/5. Try to combine like terms. Okay, so you multiply your 2/5 in. Now you can see here how I have separated it. I just do that personally so I can say, okay, I'm just going to focus on this I squared, then I'm going to focus on the 2. So when I focus on the I squared, you can see how my negative 8/125, that's just a constant, that's just a number. So it still goes in the front. And then this replaced my I squared. And then when I look at my 2, it's just, that's like your C value. So it's just going to be Cn. So 2 times n. Now personally, I didn't feel like doing a lot of algebra. So all I did here was, I know that my n is 5. You plug in 5. Just make sure you're taking your time. Don't try to plug this into your calculator all at once. And when you plug in 5, you get 6.48. So if you were to sit there, and like I said earlier, add up all the areas of these little rectangles, you would get 6.48. We were just able to do it all at once by using a summation. So looking at the next example below, it's a very similar idea, but now our endpoints are on the left. So you can see that now our rectangles are a little bit bigger than the area under their curve. So this would be kind of like what you're going to start referencing as an upper sum, because it's a little bit bigger. Our last one was a little bit smaller. So that means our area is somewhere in the middle. So when you're looking at an upper sum or something that has left endpoints, you can see that now these blue regions are just a little bit extra, right? They're going a little bit over our curve. So that means we have our area and a little bit more. So this problem is a continuation of the last one. So you can see that your endpoints are now not just necessarily that 2/5, but it's that value of that I minus 1. It's the one before it. So it's I minus 1. So 2/5 I minus 1. So when you have that, we can see that we have f of our endpoint, so that's the length, times the width. So how far apart are your rectangles? So length times width. This is our endpoints. I just simplified it a little bit, distribute the 2 on the top. Plug it into your function. Our function was negative x squared plus 5 times 2/5. And here's where your algebra comes in. So we do need to simplify this down as much as we can. So we square our fraction, combine like terms. You can multiply by your 2/5. And then you can see again how I broke it up just so that we can see each piece individually. There we go. And so once you see that, then you can replace, like, your I squared becomes this. I becomes this. This was a constant, the 242/125. That was a constant. So C, N, constant times N. Again, I did not feel like multiplying this, so I just put a 5 in for all my N's because that's what our 5 equals, our N equals. And I got 8.08. So that's telling me that my first sum, where it was a little bit less than the actual area, was 6.48. My larger sum, which was a little bit more than the area, was 8.08. So that actual area is somewhere between those two values. Now looking at this is a pretty large span, right? It's over 1. It's over 1 value. So if this was something that you needed to be accurate with, it could get better. So showing how it could get better is if you increase your value of n. So remember that n is the number of rectangles that you're working with. And that's a major idea that I don't think they actually write here anywhere. So we're going to write it right now. So it's a note for us. So note that n is the number of rectangles used. Okay, and we have talked about it where the more rectangles you use, the better accuracy you'll have. So for number 7, they're asking you to pretty much do the exact same thing, but now we're using this as 25 as our n, because they're asking us for 25 rectangles, and they're asking us right here for 25 rectangles. So if we're asking for 25 rectangles, the width of those, we're really only spanning to the value of 2 on our x-axis. So we need to divide 2 by 25. So 2 over 25 is our delta x, right here. Okay, so we still have the same function. It's still that negative x squared plus 5. Now we can find our right and our left endpoints again. We have that 2 over 25i, and then the left ones was the one before, so I minus 1. Following the same steps, you would get 7.17 and 7.49, like for that part A and part B of the example previous. So you can see that by increasing that value of n, we made that range much less, right? It went from 6.48 to 808. Now it's 7.17 to 7.49. So we narrowed that down. We got so much more accurate, and it gives us a better representation of the area. So there's our note again. I've said it many times, just so that you can write it down. It's important to remember that the more rectangles you have, the more accurate your answer will be. All right, so now let's actually really dive into this idea of upper and lower sums. So we have a plane region. So that just means that it's on the coordinate plane. It's just a two-dimensional region. It's bounded above by the graph of the function. So for instance, our last one was negative x squared plus 5. So whatever function you have. It's bounded below by the x-axis. So when we're talking about the area under a curve, it's always the area that even if our curve's a little nutty, like this, and we're concerned between the value of 0 and we'll call this value 5. It's always going to be the area under this curve but above the x-axis. So that's the region we're concerned with. So under the curve but above the x-axis. The left boundary would be the vertical line x equals a. So in this case, our a would be here. And then our right boundary is the vertical line x equals b. It's kind of like the interval that you're looking at. So we always need to figure out how to divide our area up. It's always going to be this little equation right here. There's delta x. So delta x, you can always find delta x by doing b minus a over n. And that's the interval that you're concerned with divided by however many rectangles you're trying to find. So we usually just leave n as n. And that's because you're going to find later on that we can find an accurate area by taking the limit. So we know that functions are continuous, and because of that, and because of the extreme value theorem, that tells us that we do have extrema on each function in every little interval if it's continuous. So you can see here that we have f of little m and f of big M. So when you're looking at these, you're going to hear them referenced as a minimum value and a maximum value. I don't really talk about that too much. What we're going to do is we're going to use little m for lower, which is what's notated down here, and then we'll use big M for upper. Oops, there it is. So we have our big M for our upper sum. Okay, so we have our lower sum and our upper sum. And we're going to talk about how to find little m and big M in just a minute, but this is that you know that, just think, little m, lower sum, big M, upper sum. Okay? Important notation is that the lower sum is a lowercase s, upper sum is an uppercase s. Try to really make it visible in your work when you're writing it. Really try to make the 1s much larger so that you know that that's going to be your upper sum. When you do find them, you know that your area of your graph will be between them. Okay, just like in those last two examples we did, we knew our area was between our two sums. It was somewhere between them. So it's this nice little inequality, right? So our lower sum's less than our area, which is less than our upper sum. So looking at an example of actually finding lower and upper sums, what I can tell you is when you're trying to find your lower and upper sum and you don't know your value for n, your answer will have n's in it. Okay, it'll look like an equation. So let's go through the steps here. So your first step pretty much always is to find your delta x. It's always the easiest thing to do, just get it done, get it out of the way. So you do your b minus a over n. For us, it's 2 minus 0 over n, which is 2 over n. Now, there are different ways, and these sometimes do get switched up, but make sure that, just for us, so that we all stay the same, you use these two little notes for your little m and for your big N. So we're going to stay consistent. We're going to use both of these for our little m and our big M. So let's find those. So our little m is a plus I minus 1 delta x. Plug it in, simplify. Big M, a plus I delta x. Plug it in, simplify. So that we're always going to stay consistent. We're always going to do these two for when we're working together. So it's kind of like these problems will have a part A and a part B. The first part will be using your little m, which is for your lower sum, and then your part B will be for your big M, which is your upper sum. So let's look at our lower sum first. This one's a little more complicated than the other. Okay, so we have our little m is plugged in here. Okay, now remember, this is like our length times width. That's how we find the area of a rectangle. So you're going to plug this value into your function. Our function for this problem was just x squared. So we plug this into x squared. Simplify. Remember, lots of algebra, put these together. You can always take out any constants or any numbers that just aren't necessary. If they're not an I, they can come out to the front. So if you look, each of these have an 8 in common, and this n cubed is also a number. So I took out 8 over n cubed. Now it's much more simple to look at. So we have our I squared, we replaced our I, and then 1n. So lots of algebra, right? We're combining, we're getting these into one common denominator, one fraction. Bring it all together. You can break it up by term. You can see here how I broke it up. Put 6 over n cubed over all of my terms. And then just simplify where you can. So my solution for my lower sum looks like another function, and it should. Okay, remember, n can be any value. So they could say, what's your lower sum when n is 2? And you could plug in 2. You can find your lower sum when n is 200, and you would plug in 200. Now for your upper sum, you would do the exact same thing. I actually don't think I finished this one, so we'll do this one together. All right, so we're going to finish this one out. I had to change it. Initially, I had a 5 under there. I think my mind was still on the last problem. So we have 2 over n is our delta x. So we have our summation from I equals 1 to n of 8i squared over n cubed. You can take your 8 and your n cubed to the front because they're just constants. So we have 8 over n cubed to the front. We still have the summation from I equals 1 to n. And then on the inside, we still just have our I squared. So we have 8 over n cubed times n plus 1 times 2n plus 1 all over 6. Okay, that's what we can replace I squared with. Now, as you work with these more, you will kind of like start remembering these, but until then you can just FOIL. All right, and you can just multiply and do whatever you need to do. So we have 8 times 2n cubed plus 3n squared plus n. And that's all going to be over 6n cubed. So we have 16n cubed plus 24n squared plus 8n all over 6n cubed. So I just distribute the 8 to the top. Now you can separate it. So you have 16n cubed divided by 6n cubed plus 24n squared divided by 6n cubed plus 8n divided by 6n cubed. So simplify what you can. So our 16 and 6, they become 8 over 3. The n's cancel out. 24 over 6 becomes a 4 on top. But our n squared over n cubed, that just becomes an n in the denominator. And then for our last one, you can just simplify your 8 and 6 and you get 4 over 3. And then our n over n cubed becomes n squared in the denominator. So this is capital S of n. Now you'll notice that it does look similar. Okay, I don't think you did something wrong if it looks similar. But they are a little different. So our lower sum, our little s of n, that has a minus 4 over n, and the rest are the same. Up here we have a plus 4 over n, and the rest are the same. So they are different. They're both your sums. So this was our upper sum. Hi guys, so this will be your notes filled. All right, on to the last page. So as we had talked about before, n is your number of rectangles. So as we get larger with our n values, we get more accurate. So clearly the largest number we know is infinity. So when we take our limit to infinity of these summations, you will actually get your area. Okay, so this is a way to get an accurate area, is after you find your upper or lower sum, take the limit as that's going to infinity, and that'll give you the specific area. Notice again how your delta x is b minus a over n. That's always the same, so it's nice and easy to remember. And you don't have to do both of these. If you do both, you'll find out that you're going to get the same value twice, and that's why that little equal sign's right here. You just have to do one or the other. So let's look at an example together. Now, this is a definition. There you go, definition. Area is when you take n goes to infinity. Delta x is still b minus a over n. You got that. So let's look at the example now. So I put a note here in red, and it's just because we want to stay consistent as a class. So when they're talking about your c sub I, okay, and that was in that little definition right here, c sub I, we can just all use the same value, okay? So don't worry about trying to figure that out on your own. Just always use, always use your big M, which is a plus I delta x. Just always use this for your c sub I, okay? That way we're always doing the same thing, and it'll just be more consistent. So remember, your first thing you want to do is to find your delta x. So b minus a over n, and find your endpoints. So we plug in our a and our delta x, and we have our endpoints. Now, if you follow through on here, you're going to see that we're plugging them into our function times itself. So remember, length times width. That's why we're doing this. So we plug it into our function. Our function for this problem was 4 minus x squared. So 4 minus this value squared times 1 over n. Now, a lot of algebra goes into play here. Notice how I just took the 1 over n to the front. Remove it, okay? It's just a constant. It can go to the front. It'll make it easier with less terms in your summation. So my 1 over n is in the front. I rewrote this to FOIL it. You can follow the algebra. Okay, you can see where it does get FOILed. Okay, combine what you can. And then we can take this summation. So when you do take this summation, remember this has to be 1 to n. We get 3n. Now this was 2 over n times I. So we have our 2 over n, and this replaced I. And then we had minus I squared over n squared. So 1 over n squared is kind of like our constant, and this replaced the I squared. So a lot of little algebra. Get these down into terms that you can work with. Now this one I broke up so you could see all the different limits, because it's probably been a while since you've seen a limit to infinity, or maybe you just need a little refresher. So when you're taking the limit of any number that's just a constant, your answer is just that number. Remember, it's kind of like you're looking for the variable to plug it into. So limit as it's going to 3 is 3. Minus limit as it's going to 1, minus 1. Now, when you have 1 over n, you're just plugging infinity into that for n, right? And 1 divided by infinity is 0. So anytime you have a value divided by infinity, it's 0. And then when you're looking at a limit to infinity, that's a rational function, okay? Remember our skill where what we did, we looked at our highest degree from our denominator and divide all terms by that highest degree. When you do that, you can see this is what we resulted with down here. And now when you plug in infinity, you basically have 2 plus 0 over 6. So you have 2 over 6. So we have 2 minus 2 over 6, 2 minus 1/3. 5/3 is the accurate area under the curve for this function. So remember, the key here is when you're taking the limit to infinity, and they have the same highest degree, you can always just look at the leading coefficients. All right, so I'm just going to skip to the last example. If you wanted to view the others, you can view them on this document online. So I'm going to just skip to, we're going to do number 13, the first one. So the one difference between this problem and the other ones is that now you see that our function is a function of y, and we're concerned between that function and the y-axis. So just to give you an idea of what this would look like. Okay, so you have your coordinate plane, your function, y squared kind of looks like this. And we're concerned between that function and the y-axis between 0 and 1. So we are actually looking at this region in here. So it's a little bit different visually, but arithmetic-wise and your steps are pretty much the same. So the first thing you need to do is to figure out your delta y. Same idea. So b minus a over n, and we get 1 over n. Second thing we need to do is figure out our endpoints. Same idea again. A plus I delta y, and you get I over n. We set up our area problem here, so we have the limit as it's going to infinity of our length times our width, right? Rectangle's length times width. So we need to plug this into our function. Our function was y squared. So we're plugging this in for y squared times our delta y. Simplify. We know 1 over n cubed can come to the front because that is a constant. This replaced I squared. Simplify. And again, remember what I said earlier, when it's the same degree, n cubed, it's just the ratio of the leading coefficients. So 2 over 6. 2 over 6 is 1/3. So if I were to look at this on like an actual coordinate plane, if it was drawn nicely, the part that I shaded in would be equal to 1/3. So any questions that you guys have, please feel free to reach out to me. I'll be on Zoom again on Friday and also tomorrow. So tomorrow's at 11:30 and then Friday will be at 10:45 for your class. So please attend one of them if you need extra help. If you are good to go, then that's great. But those of you that need it, that is where you can find it.